All right, so we've started talking about momentum, and we learned that momentum is defined as the product of mass times velocity, which isn't a really good definition, and it doesn't give you much to work with. But the best way to think about it is that momentum is inertia in motion, right? And we get that really from Newton's first law, where an object in motion stays in motion. So if you're in motion and you're moving at a constant speed, you're also going to have then a constant amount of momentum. And Newton's second law, with a little bit of rearranging, shows us that a force is going to cause an object's momentum to change. Um, and then if we take that Newton's second law and rearrange it again a little bit, we find out that if we apply a force over a certain amount of time, any amount of time, it's going to cause a change in an object's momentum. And that product of force and time is equal to this thing we call impulse, right? So impulse is a change in momentum. So the two things we're going to look at today, now that we have an idea of what momentum is and what impulse is we're going to look at conservation of momentum and then collisions, which is kind of the big thing, the big topic that goes with momentum. All right, so conservation of momentum is when the total momentum of a system must remain constant. All right, it needs to stay the same the whole way through. So no matter what you choose to be in your system, all right, it needs to remain constant before and after, right? So it means the sum of it. Um, so one of the things that's a bit of a typo, this should be momentum. Okay. So again, it's really important that you choose a system where momentum will be conserved. If you pick a system where momentum is not conserved, it can throw some wrenches into what you're trying to do. All right, if you're trying to solve a problem and so there's a place where momentum is not conserved, then you can't just use one of the simple little conservation momentum equations that we're going to look at. You also then need to look at the impulse that force that has not been uh, really canceled out, what that force is going to cause for an impulse or change in the momentum. So a system is a very simple thing. It's something that is really important. It's very arbitrary, but it's super powerful because it allows you to set things up the way you want it. So to make things easy for you. So when you're looking at your system, two things you need to think about are internal forces and external forces. Right? So in internal forces, so forces that are inside your system, when those forces act, they do not cause a change in the momentum of a system. So if we have two billiard balls coming towards each other and they hit, right, the forces that are involved, that force pair that is involved when those two things hit, all right, they cancel out because of Newton's third law. So one force goes one way, the other force goes the other way, and they're the same amount. So they don't cause a change in the momentum of the total system. The individual momenta of each ball may be a little different, right? Their speeds may change, but the momentum of the entire system of the two balls together, the sum of that stays the same. Now, if there are external forces that are going to be introduced or applied to the system, say that two-ball system, then they will change the momentum of the system as a whole. Right? Something like friction could be a force that is outside a system that would then change the momentum of a system. So if that's the case, right, then you will need to find out what is the impulse that is being introduced or applied to that system so that its momentum changes. Very rarely will you deal with something where there would be an outside force or an external force that is changing a system while something is occurring, right, while a collision is occurring. So really the big thing to get out of this is that momentum before and after something occurs needs to stay the same. It needs to be equal to each other. We can't lose it. We can't gain it. And that picking a system to deal with is really important towards being successful and being able to solve problems and answer questions very easily. So the real meat and bones when it comes down to momentum is collisions. All right. 9 times out of 10, if you have a problem, right, you're given a situation that involves a collision, momentum is probably going to be the way to solve it. Because all you really need to know is the mass of the system and the speed of the system, or the items in the system. So there are two types of collisions. There's elastic collisions and there's inelastic collisions. So in an elastic collision, objects are going to hit and they're going to bounce off of each other. In an elastic collision, kinetic energy is conserved. Okay? So one way you can look at an elastic collision is that there's usually no deformation to objects involved, right? So, two cars hit, this would be a weird situation, but if two cars hit and they bounce off of each other, in like the metal, like it gets crunched, and then somehow it's kind of stored as potential energy, and then all of a sudden the potential energy in the metal is released, and the shapes of the cars return back to their original shapes. Then all that energy that was crumpled, stored potential energy is then released back as kinetic energy. And if that's the case, then the momentum of the system, of the cars involved, stays the same, and the kinetic energy is also conserved. So the great thing about these elastic collisions is that when they occur, you may have like an extra variable that you can't solve for. And if that's the case, because kinetic energy is conserved, you can go try to use conservation of energy to solve the problem as well. And I'll put a video up on the website shortly after this, so where it gives a good example of how you can use conservation of energy to help solve a problem where momentum may not be enough. The other type of collision you may have is where it's an inelastic collision, and this is the case where an objects will bounce, so they hit each other and they stick. So in this case, kinetic energy is not conserved. Some of that energy is going to be released as heat and as sound, or it could be stored as some sort of crumpled potential energy. So those are our two kinds. There's also sometimes a third kind they like to talk about, which are called explosions. But I kind of like to think usually as an explosion as an inelastic collision in reverse. So you have two objects that are stuck together, something happens, and then they become separated. As opposed to an elastic is where they're separated and they collide and then they're stuck together. So it's not that difficult to kind of figure out the difference between them. So let's take a couple problems, let's look at them, let's see if we can figure out what's going on here. So the first one we're going to look at is it's problem 284 in the Knight textbook, the green textbook, and it's number 13. And it says a small 100-gram cart is moving at 1.2 meters per second on an air track when it collides with a larger 1-kilogram cart that is at rest. After the collision, the small cart recoils at 0.85 meters per second. What is the speed of the large cart after the collision? All right, so the first thing we want to do with a problem like this is we want to identify what type of collision it is, because that'll make our life a lot simpler. It gives us a little heading in terms of where we need to go. All right, so it looks here from the information they tell us where they hit and they bounce off, says a small cart recoils. That gives us a good idea. We're going to find out that this is an elastic collision. Okay, so we've got an elastic collision going on here. So the next thing we can do that's really helpful, because we've got a lot of stuff running around now, is to just list everything that we have. Okay, so if we list everything that we have, we've got one mass, we'll call it mass 1, that's our small cart, that's about 0.1 kilograms. All right, and it comes in at 1.2 meters per second. All right, so I'm calling that V sub 1I, or the initial speed of that small cart. Okay, and then we've got this second object, right, this larger cart, and they tell us that it has a mass of 1 kilogram, right, and they say it was at rest, so we're going to call that V2 sub I equal to 0 meters per second. And then they say that, all right, the final speed of the small car when it comes back is 0.85 meters per second. And that recoiled part is very important, this piece right here. That tells us that it's going to hit, the recoil means that it's hit and it's coming back the opposite direction. So because it's in that opposite direction, we're going to call that then negative 0.85 meters per second squared. And they would like us to find out what is the final speed of that larger car. Okay. So what we'll do is I'm going to call the carts, the two carts, my system, right? So that way momentum is conserved because there are no external forces changing things, right? Really the air cart, so there's no friction, right? There's no metal on metal scraping causing things to slow down. And so the only forces are when the two collide, and in that case, they cancel each other out because of Newton's third law. So what I want to do is I want to look at the momentum before the collision for each object and the momentum after the collision for each object. So every object that we have needs to have a momentum term. Right? So in that case, we have an m1 v1 initial, right? This momentum for the small car to start with before the collision, and we have an m2 v2 initial, which is the momentum of the large car right before the collision. And then after they hit, because they hit and they bounce, we then have two individual objects again. Right? Their speeds may change, right? Their motion changes, but they're still two individual objects. So we'll have then an m1 v1f, which is the momentum of the small car after the collision, and an m2 v2f, which is the momentum of the large car after the collision. So then it just becomes, from here, an exercise in plugging in the information that we have and solving for what they want us to do. So the first thing we can do, we know that the initial speed of the large car is 0, so I'm going to just make that 0. I'm just going to go through and plug in what I know. So I've got 0.1 times 1.2, all right, and that's going to be equal to 0.1 times negative 0.85 plus 1 times v sub 2f. Okay, and just a little quick math will give us what we know here. So then the final speed of the large car needs to be 0.205 meters per second. So what that tells us is that the small car is going to come in, let's say to the right, hits the large car, right, and it bounces back and goes left. Well, that large car now is going to move off to the right at 0.205. It had been negative, it would have been a little weird for it to be traveling to the left as the same direction as a small car. So you see what happens. And if we went through, we could find out that the momentum before and the momentum after are equal to 0. Sorry, not 0, they'd be equal to the same number. And there we go. That's what we've got for an elastic collision. So now let's look at a different one. Right? Let's look at what happens here. So this is on page 285 in your green physics book, the night book, and it's number 21, where it says a 300-gram bird flying along at 6 meters per second sees a 10-gram insect heading straight toward it with a speed of 30 meters per second. The bird opens its mouth and enjoys a nice lunch. What is the bird's speed immediately after it's swallowing the insect? All right, so we think about this one. We have a bird flying, we have an insect flying, and then they, for lack of a better term, they collide. And now the bird and insect are one. They're flying together. So we started with two objects, and then one gets swallowed, and now we have essentially one object. So what we're going to look at now then is, well, because things hit and they stick, we're going to call that an inelastic collision. Okay. So first thing we do, let's write down information that we have. What do we know? So we know that we have a 0.3 kilogram bird, and it is flying initially at 6 meters per second. All right, and then we have a 0.01 kilogram insect, right, and it is initially flying at negative 30 meters per second. And we're going to call it negative 30 because it's flying in a direction opposite of what the bird is. So we'll just call that the negative direction. And we would like to know, after the insect gets swallowed, what is the speed of the two things together, that system of bird and insect? So we're going to call our bird and our insect our system, so that again all the forces cancel out, or the forces that may be experienced or exerted are inside our system, so they don't change the, um, the momentum of our system. All right? So you can memorize the inelastic and elastic collisions, but I think it's easier and it's more fundamental to think about the individual momentum of each object before and after in a collision, because that way it's just a little more easier. It gives you a more fundamental view of what's occurring, rather than trying to grind out equations from memory. So if we look here, before the collision, we have a bird that is flying along, and we have an insect that is also flying along, right? And they're flying along, and then the bird comes through, and they collide, and what we're left with is the bird and the insect together. So because they're together, their masses are going to combine, right? So now the bird-insect system is the mass is the total of the two. So this is typically what you would see for an inelastic collision type problem, where you have two individual momenta, and then after the collision they stick, and the mass of that new-ish object the mass is equal to the sum of the two. Okay, so now we just go through and we start filling in what we know. So I rearrange this equation a little bit, and I find that the final speed of the bird-insect system together is going to be equal to m1 v1i plus m2 v2i, all right? And that is all divided by the sum of the bird's mass and insect's mass together. Okay, so when I do that, I can plug it in. I know 0.3 times 6 plus 0.01 times negative 30, and that's going to be divided by 0.3 plus 0.01. And we find that once you crank out the math, the bird slowed down a little bit, right? It is now flying with a speed of 4.84 meters per second. Okay, so there you go. That's an inelastic collision, right? We saw an elastic collision. You're more than welcome to remember or memorize those general equations for inelastic and elastic, but I think it's easier to, when you solve a problem, go through and just look at the momentum of each individual object before and after a collision, because I think that that sets you up a little better. So good luck, and we'll continue to do some work on momentum and collisions as we go through this unit.